So we have this problem where we have a C shape of wire with a resistor in it. We have a bar that is moving at a certain speed to the right. And the first question we're trying to ask is how much induced voltage is created by the bar? So the amount of induced voltage is given by Faraday's law, where we have induced voltage is equal to rate of change of magnetic flux. Now, right now, we don't really have a way to get a numerical value for magnetic flux. We know how tall the bar is. We know this is a height of 0.5 meter, is given over there. We know how fast the bar is moving. So even though we don't know, we can't give numerical value for finding flux, let's just see what we could do with this. So I'm going to write an initial moment, and I will say, okay, here is the loop of wire. Right now the bar is here. We know this distance is 0.5 meter, but I do not know this horizontal distance. So this horizontal distance, since I don't know, I'm just going to assign it a symbol. So I'll say this horizontal distance is L. Now, some amount of time later, we will say we have a final moment in time. And this final moment, let's suppose the bar was previously here. So this is my distance L, just like before. But let's say now at this moment later, the bar moved out a little bit. So this distance here, I will call delta x. So, okay, even though I cannot get a numerical value for the flux through my loop, I still could at least set up something that looks like the change in flux. So in general, we have the flux is directly into the board. Here's my magnetic field in both cases. And I could say, okay, magnetic flux is equal to B A cosine theta. So, what are we going to do about this? Well, okay, the magnetic flux at this initial moment, I could write as phi B initial. So B is the strength of the magnetic field. That is 1/4 Tesla. That is never going to change, 0.25. A is the area of my loop. In this case right now, area is length times width, length times height. So L times 0.5. I do not know what number L is, but I'm just going to write it in. So I could write 0.5 L. Now for the cosine of theta, we defined theta as being the angle between the direction of the magnetic field and the direction perpendicular to my surface. So the magnetic field points directly into the board. Perpendicular to the board would point into the board. So in this case, the direction between into the board and into the board is 0. So in both of these cases, the cosine of theta is going to be cosine of 0, which is just equal to the number 1. So multiply this by 1. So I could say the initial magnetic flux, phi B initial, is 0.125 times cursive L. I'm going to do the exact same thing for the final magnetic flux. So I could say phi B final. I will write that as the strength of the magnetic field never changed. So I get a 0.25. Now for the area, Well, the area has increased. So now the area is 0.5 meter times this entire distance. And this entire distance in the horizontal is cursive L plus delta x. So I could write the area as 0.5 times L plus delta x. So this is basically height times length for my area. Then I multiply by cosine of 0, that just is 1 anyway, I won't bother writing it. So when I write out the final magnetic flux, I get phi b final is equal to, okay, because I have three terms, 0.25 times 0.5 times this term in parentheses, I could factor the 0.5 in or out, it doesn't matter. But if I work out the math, I get 0.125 L plus 0.125 delta x for my final magnetic flux. Now, in Faraday's law, we only have one loop in this problem, so I am not really worrying about n here. The change in flux. I could write then that the change in flux, so we have the final flux minus the initial flux, and that is, okay, this term minus that term. So I could write the change in flux as 0.125 L plus 0.125 delta x for my final minus 0.125 L as my initial. So, okay, 0.125 L plus 0.125 delta x minus 0.125 L. These two terms, I get rid of the parentheses. These two terms end up canceling. And I get the change in flux in total for this problem is just 0.125 delta x. Now for this problem, it is, in general, if you're working through a physics problem, if you don't have a number for some type of quantity, it could be useful. Just assign a symbol to that quantity. So for example, if you have two unknown currents, we saw this very extensively when we were working with Kirchhoff's laws. If we didn't know the value of the current, we just called them I1 or I2. And then we continued solving. And instead of getting a number for a certain term, we just had a certain term multiplied by an unknown. And just assign some variable to an unknown quantity. And if that quantity is important, eventually you'll end up in a place where you could solve for that quantity. If that quantity is not important, eventually you'll end up in a place where you could just ignore that quantity entirely. So I don't know what to do about this delta x. I hope either it will somehow cancel or it will somehow end up just merging in with another quantity, or maybe we'll be able to solve for it somehow. So if you don't know, it's okay just to have something as an undetermined amount and continue. Just, you know how multiply and divide, you just carry this term along until something happens to it. So let's see what happens when we are trying to find the total voltage there. So the total voltage that is induced in this problem, I could write as total induced voltage. So the induced EMF which, like I said, for the purpose of this course is the same thing as total induced voltage, we could write as, okay, the change in magnetic flux is that 0.125 delta x divided by the change in time. I don't know what to put, so I'll just write that as delta t. Now, let's see what we can do. Well, first of all, what happened to the negative sign? The negative sign is indicative of the direction of the induced current. We're not going to worry about that until part D of this problem. For now, I only care about how much voltage is created. I only care about the magnitude of this quantity. I don't really care about the positive negative sign, if that has any meaning. So I could say the total induced voltage is going to be, let's rearrange this, 0.125 times delta x over delta t. And this term delta x over delta t, I could recognize as a speed. And we were told at the beginning of this problem, the speed of the bar is 2 meters per second. So I could write the total induced voltage is going to be 0.125 times 2. So the total amount of induced voltage is going to be 0.25 volts. And this is the induced voltage. Now, in part B of this problem, we are told, well, if you create voltage, you're going to create current. So how much current is created or induced? So for part B of this problem, I could say that, well, from before, you've seen this equation many, many times. If I have some amount of induced voltage, I will have some amount of induced current. So I could say if we create that much voltage, 0.25 volts are induced. We have some amount of induced current. I'm just going to throw on I induced as a subscript just because. We have a resistor of 0.5. And I divide both sides by 0.5 and I find the induced current is going to be I induced is 0.5 amp. So we created 1/2 amp of current in this circuit. In part C of this problem, we're asked how much power is dissipated by the resistor. The power dissipated by the resistor, you've seen that problem a lot, similar to V equals IR. We have P is equal to IV, P is I squared R, P is V squared over R. It doesn't matter what equation we use, so okay, there's one equation already written out. So P is going to be 0.5 squared for the induced current. It is just a coincidence that the resistance is the numerical same value. In general, these would be different numbers. Just coincidence they happen to be the same here. So I get P is 0.125 watts because we're talking power. Now, in the final part of this problem, we are asked, what direction does the current flow through this resistor? So, I could say that if I induced is counterclockwise, then the current is down. Because if the current is flowing like this, when it is going through the resistor, it is going to be going down. And if I induced is clockwise, Well, clockwise would be like this. And when the current is flowing through the resistor, the current would be flowing up. So here the current would be flowing up. So there are two possibilities. The current either flows up or down through the resistor, and that question is equivalent to asking, is the current clockwise or counterclockwise through the circuit? So this is how we're going to think about this. Now, even though we have a square loop of wire, we still have a good notion of clockwise versus counterclockwise. So, what we're going to do is the rod is pulled outward. And because the rod is pulled outward, there is a current that is induced from the induced voltage. And because we have an induced current, we'll have an induced magnetic field. So we want to know what direction will the magnetic field point in this problem. So I could say as the rod is pulled to the right, the first question I ask myself is, what will happen to the magnetic flux? The magnetic field points into the board, and as the rod is pulled, that would tend to increase the magnetic flux. So as the rod is pulled to the right, that means the area increases. And because the area is increasing, the magnetic flux will increase. Now, Lenz's law says that nature opposes a change in magnetic flux. It's not that nature tries to increase or decrease magnetic flux. Nature just opposes the change. So Lenz's law says nature opposes a change in magnetic flux. So, let's think about this. If I want to, now ignore this problem for a minute, we could keep the same picture. If I want to change the magnetic flux without ignoring rotation, there's two things I could do. I could change the value of the magnetic field, or I could change the size of the loop, change the area. So in this problem, I will have two magnetic fields. I have my original magnetic field, the 1/4 Tesla that we have been working with since the beginning, but I'm also going to now have this new magnetic field. So I have my original magnetic field, and I will have an induced magnetic field. And the induced magnetic field is going to contribute to a flux that tries to oppose change. So I'll say it is the induced magnetic field that will oppose this change in magnetic flux. The first magnetic field is already set. We're not allowed to change it. It is what it is. It is created by something else, and we have no control over what it does. This induced magnetic field, we have two options. The magnetic field could either point into the board or out of the board. So let's think about those options. I said before in a lecture when I was talking about the direction of current in a loop of wire magnetic field. If you have a loop of wire, you have two choices. The current in that loop of wire could flow clockwise or counterclockwise. There's no third option here. So if I curl my four fingers of my right hand, I could have my four fingers curling clockwise or counterclockwise. In this case, my four fingers are going to be the current because the current flows through the wire one way or the other. If my four fingers are curling in a clockwise direction, well, my four fingers in this case are going to be the current because that's the loopy part. My four fingers curl clockwise, my thumb points into the board. If my four fingers are the current, my thumb must be the magnetic field. Because my four fingers were already assigned to be current, my thumb must be B. So clockwise, the induced magnetic field will point into the board. Counterclockwise, the induced magnetic field will point out of the board. So let's think about this. The induced magnetic flux, the new magnetic flux, the magnetic flux represented by my thumb wants to oppose a change. So the induced magnetic field represented by my thumb wants to try to prevent a change in magnetic flux. So the magnetic flux is pointing in, the magnetic field is pointing into the board. It's not proper to say a magnetic flux has a direction, but if for the moment I think about the magnetic field lines are pointing into the board, as I pull this bar to the right, there will be more and more magnetic field lines pointing into the board. Nature is going to oppose that increase in magnetic flux. So nature wants the magnetic flux to decrease. So one way nature could do that is if I have a second magnetic field, if my original magnetic field points into the board, if I have a second magnetic field that points out of the board, that would tend to decrease the strength of the magnetic field, which would in turn decrease the flux. So I could say if B induced, I'm using a subscript induced, points out of the board, that would tend to decrease the flux. So B total would be smaller. The total magnetic field is the original magnetic field plus the induced magnetic field. If B total is smaller, that would imply the flux will be smaller. Right now, as the bar is being pulled outward, the flux is growing, and nature is going to oppose a change in flux. So if the flux is getting bigger and bigger, nature wants to keep the flux smaller. That implies we want B total to be smaller. Nature has no control over what is happening to the area, but nature can determine what direction the induced magnetic field is going to point. So nature is going to have this induced magnetic field point out of the board. Now, because I have a loop of wire, my four fingers will be the curly part, the loop, that's the direction of the current. I align my thumb out of the board, and whatever direction my four fingers curl, that's the direction of the induced current. So my thumb is out of the board, my fingers are curling counterclockwise. So I could say when my thumb points out of the board, then my four fingers, which is the current in this case, curl counterclockwise. Oh, Lenz's law is important. I'm just going to keep that right there. And if my four fingers are curling counterclockwise, that implies that the direction of the electrical current is going to be something like this. So the current will flow this way. This is I induced. And specifically, when the current is flowing through the resistor, the current will flow down. So that implies that I induced flows down through the resistor.